This is CX1104, section 6.2.3, orthogonal sets and orthogonal bases. Orthogonal sets. Here we are dealing with a set of vectors. For example, U1 to UP in Rn means U1 belongs to Rn as well as U2 belonging to Rn, and so on. When we say they are, in addition to being a set, they are also orthogonal, what we are saying is that the vectors ui dot uj will result in 0, showing that ui and uj, if I is not equals to j, they are perpendicular or orthogonal to each other. Let us see an example in example 1. We have u1 with 311, u2 with this value, u3 with this value. They are all these u1 to u3 belongs to R3. To show that they are orthogonal to each other, we will compute u1.u2, u1.u3 as well as u2.u3. We do not need to compute u3.u2 because, as you will see, dot products are symmetrical, and therefore u3.u1 is also the same as well as u2.u1. The brute force approach to compute the dot product is shown here, showing that all of these dot products result in 0, showing that all these pair of vectors are orthogonal to each other, and therefore we again say that this u1, u2, u3 forms an orthogonal set. The most common example of R3 when n equals to 3 is this set of orthogonal vectors. Immediately it is obvious that the column 1 is orthogonal to column 2, is orthogonal to column 3. Visually it is also very satisfying. We see that the first column I, which is 100, is 90 degrees to the second column 010, which is also 90 degrees to the third column 001. So let's visit the definition again. Orthogonal set is a set of vectors such that all pairs are orthogonal to each other. The vectors u1, u2, and so on, up, all belongs to Rn, n-dimensional vectors. However, P does not need to be equals to n. If P is equals to n, then we have a set of vectors that forms a basis for the Rn space. If P is strictly less than n, then we only have P number of column vectors that span a subspace of Rn. Let's digress a bit to understand the definition of a basis. A basis is a set of independent vectors that spans a vector space. Here, the vector space can be a complete vector space or a subspace. We now need to define what is independence and what is span. In the previous lectures, you have independence means that two vectors are not scalar versions of each other if we only have two vectors. When we have more vectors, it means that linear combinations of these vectors cannot become one of the vector in this set. And lastly, the word span. Span basically means that it is the linear combinations of the given vectors. I should say all linear combinations of the given set of vectors. So in this theorem, it is claimed that orthogonal set of vectors non-zero vectors is linearly independent, and therefore, because they are linearly independent, they can become a basis for a subspace. And this subspace is sent by S, where S is the set of the orthogonal vectors u1 to up. The proof is following the following strategy. On the left hand side, we have the zero vector, and we say that the zero vector can be formed by some linear combinations of u1 to up. If all the c1, c2, the scalar multipliers of this u1 to up needs to be 0, so that the right hand side is 0 and the left hand side is also 0, agreeing, then u1 to up are linearly independent. In other words, there is no way we can get the zero vector except all 0 multiplying with u1 to up. If this is true, then u1 to up are linearly independent. So let's proceed. Let's assume on the left hand side we have the zero vector, which is the both 0, and the right hand side we have the representation decomposing the zero vectors into c1 by u1, c2 by u2, all the way adding to cp by up, and we have not fixed any values of c1 to cp yet. It will be any arbitrary values. On the left hand side, we multiply by, or we dot product with u1, and therefore we are also dot producting with the right hand side. Remember that u1 and up are orthogonal, meaning u1 dot u2 is equals to 0, and so on. We open up the expression, we bring u1 into this, and we open it up. Therefore, now we have c1 u1 dot with u1, c2 u2 dot with u1, and of course the last term cp up dotting with u1. Remember that u2 dotting with u1 is 0. up dotting with u1 is also 0. In fact, all the other u's that are not u1 dotting with u1 will give you 0, leaving with us only the first term here. We can open up the brackets. c1 is the same as u1 dot u1, and we remember that u1 dot u1 is the norm square of u1. u1 is also not the zero vector. Therefore, this u1 dot u1 is non-zero. However, on the left hand side, we want to have the 0. On the left hand side, we have the 0 value. What happened is that it is a 0 value because it is the 0 vector dotting with u1. To get the scalar to be 0, what we need is c1 to be 0. And this can also be proved for c2 all the way to cp. And hence, we now can see that, or we have proven that the set of vector S, when they are orthogonal, they are also linearly independent.